Class. Okay, so the good news is if you learn how to solve binding energy problems, you'll be able to do the rest of the chapter. All there is problems like binding energy problems. And then there is nuclear decay, which is exponents, et cetera, and logarithms and stuff like that. So yeah, anyway. So concept 0 is that you got to understand that in physics, the thing we deeply care about is not so much the chemical properties of something, but what's in the nucleus. And so we understand that there's protons and neutrons in the nucleus, but not all nuclei are made the same. And so what you see on a periodic table is just a mishmash, an average of all the isotopes. So for example, chlorine is 35.453. Well, gee, protons and neutrons have a mass of almost exactly 1. Right, so how do you get 35.453? Well, there's some mixture of 2 different isotopes going on there, right? Carbon is 12.011. Well, carbon actually defines what an AMU is. Sorry, I'm getting kind of emotional here. It defines what it really is, okay? So it is actually, carbon-12 is exactly 12. It defines what 12 is. In fact, an AMU is 1/12 of a neutral carbon atom, right? So the fact that they're putting 12.011 means that naturally occurring carbon is a mixture of carbon 13 and 14 and carbon 12, right? So let's just look at the notation here. And I think you've got this on your little note guide, don't you? Yeah. Right? So A is the mass number, right? So if we've got carbon 12, okay? That's the mass number. This thing here is the number of protons plus neutrons. Okay, so that's the mass number. These are all, by the way, integers. They're always just in, an even integer, right? Because you either have a proton or a neutron, or you shut up and pay attention. Don't, right? It's not something you sort of have, right? Because we're talking about a particular nucleus here. This is this guy here is the proton number, which is also, by the way, the atomic number. This means the same. 6 means the same as carbon. Carbon is 6. 6 is carbon, right? Okay. So you don't need to say 6 carbon 12. You can just say carbon 12. It's like 1 atom 5 or something like that, right? Okay. So this guy is our A. This guy is Z, is what we call it. And then how do you figure out the number of neutrons? You have to subtract. Yeah. So the neutron number, the number of neutrons is going to be A minus Z. So in this case, this is just a happy little family. 6 protons, 6 neutrons, 6 electrons, makes a neutral atom, and 6 dogs, and 6 cats, and 6 apple pies. Yeah. I know. There it is, right? So carbon-12 has 6 neutrons, but it's not the only carbon in town. There's carbon-14, which I believe is created in the Earth's atmosphere by cosmic rays. Come down and make carbon-14. It's unstable. It has a half-life of about 5,730 years approximately. Okay, and it's sort of an interesting thing, right? Because carbon-14, because it's got that half-life, it can be used to measure the age of things that are thousands of years old. And the way that works is that you right now are breathing in carbon-14. It's chemically the same as carbon-12. Okay. But it's unstable, right? So it's becoming part of your body, right? And then when you quit ingesting carbon and go into that great yonder, okay, your body, whatever carbon-14 it has, it's all living things have about it in the same proportion, and then it decays. The carbon-14 will decay. And you can measure, if you can carefully measure the ratio of those isotopes, you can measure the age of something. And the older it is, the harder it is to measure the age. And then also sunspot activity and sun cycles change, I believe, the carbon-14 concentration. I don't know. There's corrections to it. There's old carbon dating, new carbon dating, right? So this is called an isotope. Isotope means, I think it means like same place or something. I don't know. You'll have to look at that, the meaning of it, right? So if it's a different thing that fits on the same place on the periodic table is what it means. So chemically, this thing is identical. But it's nuclearly different. Nuclearly, that's almost impossible to say. Nuclearly. Nuclearly? Yeah. Nuclearly. So that's our first thing that we got to learn is how do you in order to figure out binding energy, you have to be able to figure out number of protons, number of neutrons. So that's our first thing. Whiteboard, baby. So what's the atomic notation for tritium? Tritium is an isotope of hydrogen. And tritium is hydrogen with 2 neutrons. Hydrogen doesn't ordinarily have. There's also deuterium. I don't know when you want to go. Probably not at all this period, but it's up to you. That's right. Maybe now. This is pretty easy. There you go. Yep. Yep. Write it down on a whiteboard. That's right. Hold it over your head. That's right. Well, I'll get you a whiteboard. That's right, that's right. Yes, yes. 3 up top, 1 down below. Yeah. Uh-oh. Dinner do. Dinner do. Time to go to school. That's right. Yes. Oh, this is hydrogen.
Is that right?
X is an H.
Oh, you put the... Oh.
Yes, you do. That's right. Huh? I do.
That's true.
I only have black now.
What are the prices like these days?
$1. Yeah. They cost more than $1. Yeah, they do. That's right. There you go. Don't lose that pen.
I don't. I understand why Murray's cut out explosives.
There you go. I've cut out explosives. Are we ready for the next one?
Yeah.
Yeah, you got it. 10 protons, 12 neutrons. What is its atomic notation? I'll tell you this. Atom number 10 is neon. Ni. 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 Yeah, you got it. Yes, 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 yes.
Oh, and
Yep, 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 yep. Ni. That's right.
Why is that it?
Yes. Shrubbery, yeah, put a knee next to it. That's right. Paula Collins, Paula Collins, Paula Collins. Show me your answer. If you don't, I'll keep singing this song. That's right. Show me the answer. Yeah.
So why am I expert?
Oh, Hanabigesh. That's right. Are you ready for the next one?
Yes, I am.
Nothing prepares you for the next one. How many neutrons in uranium-235? What would be handy to know?
What's uranium's atomic number?
What's its atomic number? It is 92.
235.
Yeah. What is it?
That's 143.
Write it down. What units? No, I'm just kidding. Yeah. Why? That's right. Why is carbon stable with the same number of protons as neutrons? That's right. That's right. That's right. But uranium can be stable only with buttloads of neutrons. Yes, 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 yes. Jimmy Neutrons. That's right. Yes, yes. Yeah, you got it. Yeah. You don't have to write units. Why does uranium need so many neutrons? Yes, sir.
Because none of the
Right. The problem is that you get the atom starts to get big. The strong nuclear force that binds the atom, boys and girls, the strong nuclear force that binds the atom starts to break down at long distances. So in large atoms, right? You need to add neutrons because they don't add repulsion, correct? Neutrons don't add repulsion. They're neutrally charged.